Hello again, physicists. Today's video is on Newton's Law of Gravitation. This is the final topic in our circular motion unit. So, let's jump right into it. Isaac Newton. You probably know him for the apple falling on the head and his discovery of gravity. And he did recognize that this force that caused the apple to go towards the Earth was the same force that kept the moon in orbit with the Earth. And he gave that force the name of gravity. So gravity is this invisible force that attracts masses. He also was able to specifically, though, establish some relationships between properties of the objects, their positions, and how strong that gravity was. He recognized that the larger the masses were, the larger this force of attraction was. And the further away these masses were from one another, the smaller this force of attraction would be. And this allowed him to eventually arrive at his formula for how gravity works universally. Based on Newton's observations about how mass and distance affected this force of gravity, he arrived at this equation right here. And we've seen this in class from our own investigations. So on the left-hand side, this is the force of gravitational attraction between two masses, and it will be equal to this capital G, which is the universal gravitational constant. This is a consistent value that is located on our equation table, and it is 6.67 times 10 to the minus 11 meters cubed per kilogram second squared, which may seem like weird units, but essentially it's so that the dimensional analysis of this entire thing leaves you with units of newtons. So this is the gravitational constant. It's a number. It's not something that needs to be memorized. In addition, we have this constant multiplied by m1 and m2, and these are denoting the two masses who are attracted by gravity shared between one another. So m1 and m2 could be any two objects. They could be you and your computer that you're watching this video on. m1 and m2 could be you and the Earth. It could be you and your favorite pet dog, because as long as there are two masses in existence, they will share a gravitational attraction towards one another. And then finally, this entire thing is divided by r squared, where r is the distance from the centers of the two masses. And that is important to note, that it's the distance between the centers of the two masses, especially when we're going to be doing calculations with this equation involving large objects such as the Earth or the Moon. Here we can see graphically again what Newton had observed. If I increase the mass of m1, just one of the objects, we'll see that the gravity between the two objects will increase linearly. Similar thing will happen if you increase the mass of m2. And if we increase the distance between those masses, we'll see that the gravity between them decreases, and it decreases in a nonlinear fashion. Specifically, if I were to say double the distance between my two masses, it would cut the force of gravity between them by a factor of 4. So to give you an idea about just how strong gravity really is, we're going to use Newton's law of gravitation to calculate the gravity shared between two everyday sized masses that are an everyday ordinary distance separated from one another. In this case, we're going to look at the gravity shared between two 1 kilogram masses that are separated by a distance of 1 meter. A realistic scenario to visualize here would be perhaps two textbooks sitting on a desktop, that are separated by about 1 meter, so they'd be on either side of the desk. They do have gravity between them. Let's find out how strong that gravity would be. So the first thing would be, I would take my universal gravitational constant of 6.67 times 10 to the minus 11 meters cubed per kilogram second squared. And again, that is the same regardless of the situation. And then what will be different on a case-by-case basis are the two masses involved. In this case, M1 and M2 are both 1 kilogram. And that would be divided by the distance by which they are separated. Again, this would be measured from the center of each object. In this case, it's 1 meter. Whole thing squared. And then if we number crunch that, we have the gravitational constant times 1 multiplied by 1 again, divided by 1 squared, which is 1. So in this situation, the force of gravitational attraction between these objects is 6.67 times 10 to the minus 11 newtons of force. That is roughly a millionth of a newton. And a newton itself is a pretty small force. So gravity is a weakling. It is not significant on everyday scale. And really, you only see gravity manifest itself as a meaningful force when you have large objects, at least one large mass, that is within close proximity. We just conveniently to have a very large mass that is very close to us, and that is the planet Earth. Okay, let's try a relevant application where circular motion would be part of the problem. This would be orbit. There are specific cases of orbit where the object that is orbiting is in circular motion and the centripetal force involved is gravity. Now, because we're not near the surface of the Earth necessarily when we're in orbit, we need to express gravity using Newton's universal law of gravitation. So what we'll do is use Newton's law of gravitation to figure out how large that centripetal force will be in newtons in this case. And we're also figuring out what the astronaut's weight is, because a common misconception, and this is like a dire mistake made by even the people that are in charge of NASA. They like to say that you're in a weightless environment, or even they'll call it a microgravity environment. And the truth is, even when you're in orbit above the Earth, you actually have a significant fraction of your weight retained, and it's a pretty simple calculation to prove. So we're going to use Newton's law of gravitation as we've seen it before. G will be our gravitational constant, as it always will be. M1 and M2, in this case, will be the mass of the astronaut as well as the mass of the Earth. So I'm going to do capital M subscript Earth for the mass of the Earth. Capital M since it's clearly going to be the larger mass of the two. And then we'll do lowercase m subscript astronaut. And this will all be divided by the difference, or the distance, excuse me, between, remember, it's the center of the astronaut to the center of the Earth. That's important, because even though the astronaut is 500 kilometers above the Earth, that is only measuring to the surface of the Earth. You still have the entire radius of the Earth to take into account as well, and that is a very significant distance. So when you do the distance part, it's going to be the radius of the Earth plus those 500 kilometers, which in meters would be 500,000 meters. Now, the radius of the Earth is about 6.37 times 10 to the 6 meters. And then the mass of the Earth is about 5.98 times 10 to the 24 kilograms. So with those two values, and having been given the mass of the astronaut, we can figure out what his weight, what his force of gravity he's experiencing is in newtons as he is orbiting. So pause, take a moment to do this calculation, and then we will see how you did. So if you did the calculation correctly, you should have gotten a force of gravity of about 846 newtons pulling on that astronaut while he is in orbit. Whereas, to compare it, if he was standing on the surface of the Earth, his weight would be about 980 newtons. So clearly you can see that this astronaut is not weightless. He is feeling the pull of gravity. Furthermore, he still maintains a significant fraction of the same gravity he would feel if he was on the surface of the Earth. The reason why they look like they are weightless when they are in orbit, those astronauts, is because they are in perpetual freefall, along with the space station or shuttle or whatever they're on. So it gives the illusion of weightlessness, but they are not actually weightless. That's it for today. Until next time, physicists, until next time.